Hey guys, I'm going to go ahead and do number 17, 18, and 19 with you. I've already started working on 17 as we started it in class. So f prime of x is 1 minus 4 over x minus 4 squared. And we have critical values or critical points at x equals 6 and 2 because that's where f prime of x is equal to 0. So if you do set that equal to 0, you should be getting 6 and 2. Please do it on your own and check that you get the same answer. And then a critical value also at x equals 4 because that's where f prime is undefined. So remember, critical values or critical points are where the derivative is equal to 0 and also where the derivative is undefined. So we test these critical values, and I'm putting 0, x, and 0 just to show that that's where it's undefined or infinite, and 0 and 0. And we test values within these intervals, and we should be getting plus, we should be getting minus, minus, and plus. So you're going to test values. You could test 0, you could test 3, 5, 7, plug it into the derivative, and you will find plus, minus, minus, plus, and you do have to be able to do that by hand. So we are increasing, our function is increasing from negative infinity to 2 and from 6 to infinity. And we're decreasing from 2 to 4 and from 4 to 6. Now the reason why we're stopping at 4 is because we do have a vertical asymptote at 4, and we could see that right from the beginning that we're going to have a vertical asymptote at x equals 4, because we have an x minus 4 in the denominator. All right. We have a relative minimum at x equals 6. So we have here a minimum because we're going from decreasing to increasing. And we have a maximum at 2 because we're going from increasing to decreasing. So at x equals 2. All right. Now x equals 4 is neither a max nor a min because nothing's happening there. You know, it's just decreasing the entire time. So that's our analysis of the first derivative. Now to analyze the second derivative, we found the second derivative, and if we set it equal to 0, we will have nothing. It'll get 0 equals 8, so that doesn't work. So the second derivative, I'm sorry, cannot be 0, but the second derivative is undefined, so it is undefined when x equals 4. So we need to check that to see concavity. Now, x equals 4 cannot be a point of inflection because the second derivative is, well, mainly because there's no point at x equals 4. X equals 4 is a vertical asymptote. It's not going to be a point of inflection, but we will be able to see where it's concave up and concave down, and that will happen. That will help us when we start to graph these. So at x equals 4, we have undefinition. So before 4, if we plug in like 0 into the second derivative, oh, that should be to the third. Sorry about that. All right, if we take the second derivative of that, this will become to the third power. So if we plug in 0, we're going to end up with a negative. If we plug in 5, we're going to end up with a positive. So we are, f of x is concave up from 4 to infinity, and it's concave down from negative infinity to 4. There is no inflection point, so no point of inflection. Because f of x is undefined. F of x is undefined at x equals 4, so no point of inflection. And we do have, like I said, a vertical asymptote at x equals 4. They do want us to check end behavior, so the limit as x approaches infinity of f of x. I'm going to check the limit as x approaches negative infinity of f of x. Okay, let's ignore this for now. So the limit as x approaches infinity of this. Well, as x approaches infinity here, we have infinity plus 0. Why is it plus 0? Well, because this is bottom heavy, and as x approaches infinity here, we get 4 divided by an infinitely large number, so it becomes 0. So that's just infinity plus 0, so it's infinity. And as x approaches negative infinity, okay, as x approaches negative infinity to x, it's negative infinity. And 4 divided by some infinitely large and negative number still is going to get close to 0. You can plug in negative 1 billion, negative 1 trillion here, and you're going to get 4 divided by some really large negative number is still going to be getting closer and closer to 0. So negative infinity for this guy plus 0, bottom heavy again, is negative infinity. All right. So as x is getting infinitely positive, y will get infinitely positive. As x is getting infinitely negative on this function, y will get infinitely negative. Now we're not sketching these just yet, but what you can do now is graph this in Desmos and check that everything you said about the function is true. So we are saying things about the graph of this function, so you can graph it now in Desmos or on your graphing calculator and check that everything you said about it is indeed true. All right, for number 18, we are going to go ahead and find the derivative. We're going to set that derivative equal to 0, so we end up with secant squared x is equal to 2. And we're going to take the square root on both sides, so we get that secant x is equal to plus or minus square root of 2. Now you may want to pull out your unit circle to help you out here for multiple reasons coming up. So let me go ahead and take out my unit circle. All right, here we go, ladies and gentlemen. This needs to be done eventually without this, so you need to go back and memorize this. Do not make me give you a unit circle memorization quiz. I did that to them last year. I will do it to you this year if I don't see you starting to memorize this unit circle again. Okay, you have been warned. I know I don't have it perfectly memorized, but I have strategies for figuring it out, and you should be doing the same. Also, you are the one taking the test. So anyway, secant of x is plus or minus square root of 2. That's 1 over cosine of x equals plus or minus square root of 2. So we're looking for where cosine is square root of 2 over 2. If you manipulate this to isolate cosine of x, sorry about that, to isolate cosine of x, you're going to be looking for where cosine of x is equal to plus or minus 1 over radical 2, which is radical 2 over 2, rationalized. So cosine is radical plus or minus radical 2 over 2 rationalized at pi over 4 and 3 pi over 4 if we're looking only at the interval from 0 to pi. All right. So we've got critical values. Let me minimize that a little bit. All right, we've got critical values at x equals pi over 4 and 3 pi over 4 because f prime of x is equal to 0 there. But we also have critical value where f prime of x, let's see, because f prime of x is undefined. There is a place where f prime of x is undefined because f prime of x is 2 minus secant squared x. And last I checked, this is 1 over cosine squared x. And right here, at pi over 2, cosine is 0. So we have undefinition, so x equals pi over 2 because f prime of x is undefined. So if we take our sign chart, at pi over 4, pi over 2, and 3 pi over 4, and this is where the unit circle will also help you. You can plug in 0 for here. And then between pi over 4 and pi over 2, you can plug in pi over 3, and this is where knowing the unit circle helps, and we dealt with this in 7th period today. You can plug in pi over 3 between pi over 4 and pi over 2, so let's just write, we're going to plug in 0. We're going to plug in pi over 3. Between pi over 2 and 3 pi over 4, we'll plug in 2 pi over 3. And then over here, we can plug in pi. And this is where the derivative was 0, and this is where the derivative was undefined. Now, again, knowing the unit circle helps us to come up with these values, all right? It's just part of the package. So when we plug those green values into the derivative to get our signs, we end up with plus, minus, minus, and plus. So you can write this for yourself, but we are increasing from 0 because we are starting at 0. We're increasing from 0 to pi over 4 and from 3 pi over 4 to pi. And our function is decreasing from pi over 4 to pi over 2 and pi over 2 to 3 pi over 4. Pi over 2 is going to be a vertical asymptote, guys, because literally this cannot be pi over 2. This cannot be pi over 2. So 2x minus sine over cosine it cannot be pi over 2. All right. So we have a vertical asymptote at pi over 2. If you plugged pi over 2 into the function, it would be undefined. And we have a relative minimum. This is going up to down. So we have, relative maximum. Relative maximum at pi over 4, increasing to decreasing, so relative max. And decreasing to increasing, we got a relative min at 3 pi over 4. So now let's talk about the second derivative. And keep my unit circle there. Okay, our second derivative is the derivative of the first derivative. So we're looking at 2 minus secant squared x. So we've got to do a chain rule with some trig. So bring down that, we're going to rewrite this as 2 minus secant x squared. Derivative of 2 is 0. So the second derivative is going to be negative 2 times secant x to the first power times the derivative of secant, which is secant x tan x. So my second derivative is equal to negative 2 secant squared x times tan x. Okay, there is my second derivative, and I want to go ahead and set that equal to 0. So I went ahead and set it equal to 0, divided off that negative 2. This is what we're looking at with secant squared x and tan x. So if we multiply off cosine squared x and cosine x, we end up with 0 is equal to sine of x. Now we know that sine of x is 0 at 0 and at pi, but those are endpoints, and you cannot have a point of inflection on an endpoint of a graph. That doesn't make sense. So that's not going to work for us in this particular case. Okay, setting f double prime of x equal to 0, we're not going to yield anything because those points are on the endpoints, and we're looking for points of inflection. That's not going to happen on the ends of the graph. But is there a place where perhaps 1 over cosine, I guess to the third x, or let's call it sine x over cosine to the third x, which is that guy right there, is there a place where that is undefined? Is there a place where this is going to be 0 on the interval from 0 to pi over 2? Yes, right there on the interval from 0 to pi, and yes, it's going to happen at pi over 2. When x is pi over 2, f double prime of x is undefined. So we need to test it as a possible point of inflection. Well, it's not going to be a point of inflection. Why? First of all, because f double prime of x is undefined there. Second of all, because we already decided we had a vertical asymptote. We should have written that down. We have a vertical asymptote at x equals pi over 2. Because x equals pi over 2 makes tangent undefined. But we do want to check for concavity to the left of that asymptote and to the right of that asymptote. So if we plug in to the left of pi over 2, we have negative. If we plug in to the right of pi over 2, we have positive. So f of x is concave up from pi over 2 to pi, which is the endpoint, and f of x is concave down from pi over 2 to, or from 0 to pi over 2. We have no inflection point. Like I said, we have a vertical asymptote at x equals pi over 2. And the limit, the last thing they ask you for is a limit as x approaches positive or negative infinity. It does not exist, okay, because these are periodic functions. They repeat and repeat and repeat and repeat, so there is no end behavior. Remember, on trig functions, there's no end behavior. And you can graph f of x now and check to see if everything you said in this mess here, if everything you said is correct. Now let's take a look at 19. 19 says, let L be a function representing the number of people in line for a ticket. So L represents number of people in line for a ticket. What can be said of L prime and L double prime? The line is getting longer, so the number of people in line for a ticket is increasing. That has to do with the first derivative, and that means that the first derivative is positive. The line is getting shorter. That means the number of people in line is decreasing. That has to do with the first derivative, and that means that it's negative. The line's length isn't changing, so the number of people in line isn't changing. That has to do for the first derivative, and that's the first derivative of 0. The rate of change the rate of the change in the line is increasing. So the change of the change in the number of people is increasing. The rate of the change in the line is increasing. That's your second derivative, the derivative of the derivative, and that's positive. The change of the change in the line is increasing. Now let's talk about E. In E, the line is getting longer, but at a slower rate. So the line is getting longer means that the first derivative is greater than 0. And now we're talking about the rate that the line is changing. And when we're talking about the rate that the line is changing, or the change of the change, we're talking about the second derivative. Okay, so is the second derivative greater than 0 or less than 0? Well, it does say the line is getting longer, so the derivative is greater than 0, and at a slower rate. So the second, that's happening at, if that's happening at a slower rate, then the second derivative is smaller than 0. But let's go ahead and take a look at some possible points and kind of prove that that's true. So over time, I went ahead and did, 5-second intervals. Is the seconds? T. Yeah, T is time. So let's say minutes or seconds, whatever. So over time, this is the number of people in the line, and I kind of forced this to happen. Notice I just randomly picked these points. So in this situation, L is increasing, 10, 15, 8, 20, 21. But the change in L over each interval, the change in L is decreasing. So it's going from, that's the change is 5, going to 3, going to 2, going to 1. Okay? So notice how even though L is increasing, the change in L, or the second derivative, the change in L is decreasing. If you were to graph these points, I know these are samplers, but they do model the situation on E. If you were to graph these points that we just modeled, you would see an increasing curve. You would see an increasing curve that is concave down. Okay, so if you were to graph those points, you would see an increasing curve that is concave down. Now F is the harder one to analyze, so we're going to analyze that one now. Okay, so F is saying the line is getting shorter, but at a slower rate. So let's take a look at these two pieces of the sentence. The line is getting shorter. If the line is getting shorter, that means that the first derivative is smaller than 0. The first derivative is negative, okay? But when we're saying at a slower rate, over time, what we're saying that the slower rate over time means that the change is less negative. Because the change is already negative, but it's happening slowly. So since it's a slower rate over time, the change is less negative. Let's see some points to help us visualize that. So let's say 0, 5, 10, 15, and 20 for time, and let's grab 25, 20, because it is decreasing, 17, 15, and 14, okay? So now L is decreasing. As we said, the line is getting shorter. But the change in L over each of these 5-second intervals, okay, is going down 5. It's going down 3. It's going down 2. It's going down 1. Okay? So the line is getting shorter, but it's getting shorter at a slower rate. So this change is getting less and less negative. It's kind of like when we talk about velocity and acceleration. Okay, remember that velocity is the first derivative and acceleration is the second derivative. And we can have a negative velocity, and if it's slowing down, that means that we had a positive acceleration. So since it is slowing down, and this is kind of like, this is the first derivative, the line is getting shorter, that's the first derivative being negative, kind of like saying the velocity is negative, right? But at a slower rate, that means that the second derivative has to be the opposite sign, because when these are opposite signs, it slows the process down. The rate is being slowed down over time. So think about kind of like velocity and acceleration here. They are, same thing here, line is getting longer, so our first derivative is positive, but at a slower rate, so our second derivative was negative because they had to be opposite signs since it was slowing it down. And that slowing down process is when the second derivative is that opposite sign of the first derivative, and to verbalize it, it's that the change is, when we're slowing down, the change, in this case, in F, the change is less negative. Okay, the change is less negative. As this slows down, as 25, 20, 17, 15, 14, as that slows down, the change between them gets less negative. And if you were to graph these points, if you were to graph that, those sampler points, I move that out of the way. If you were to graph that, you will get a decreasing curve that is concave up, okay? You will get a decreasing curve that is concave up. So I hope that that helps you think about E and F. You can connect it back to velocity and acceleration, where velocity is the first derivative of the function, of the position, and acceleration is the second derivative. And acceleration and velocity combined tell you about speeding up and slowing down, because acceleration is the rate of the rate, or the rate of change of the rate of change. So since the line is getting shorter, that's a negative first derivative. But at a slower rate, if it's slowing it down, then the second derivative has got to be positive. I hope that helps you with number 19. Thanks.